Hey everybody, I wanted to get into a topic that is near and dear to my linear algebra class's heart right now because we are studying eigenvalues, eigenspaces, and eigenvectors along with characteristic polynomial. And the burning question on everybody's mind is Whygenvectors. Why are we doing all of this? So I've cooked up a little example that I hope gives you some idea of some of the motivation behind, Weigen stuff. So let me paste this here. I've got a little setup. I've got a linear operator. So it's a function that goes from R2 to R2. And linear operators are great because we can apply them over and over and over again to the same space and see what happens as we iterate them. And I made up this tiny example. It's a nice toy example. We're going to see that the arithmetic works out nicely when we calculate eigen stuff. But what it's doing is it's taking a vector xy and it's multiplying it by this matrix where the first row is 2, -1, and the second row is 4, -3. So everybody loves the standard basis for R2, and that's fine. You're allowed to love the standard basis. We're going to plug this into our linear transformation, evaluate it, and see what we get. So if I plug in 1, 0, that's going to give me just the first column of that matrix back. And so I get that the vector 1, 0 gets transformed to the vector 2, 4. And I will attempt to draw that vector here. So there's 1, 0, and it gets transformed to 2, 1, 2, 3, 4. So it gets transformed to something like this, which is quite a bit different. Like, if I were saying, are these vectors similar or not, I'd say, oh, they're pretty different because they point in different directions, and they're not even like nice different directions, like perpendicular to one another or something. It just takes 1, 0 and it just whoop goes in a totally different way. So I get the vector 2, 4 out of that. If I look at what happens to my other standard basis vector, 0, 1, I'm going to get -1, -3 out of that. And so that takes this vector. I go -1 in the x direction and -3 in the y direction. Sorry, pardon the cat. And that sends my vector down here. And again, this is like a significantly different vector than the one we started with. And so if I think about what's going on here, if I give you the vector, I don't know, let's pick a vector. Let's say like 1/2 and -1, and I want to know what L does to this thing. Well, I can take L and I can break it up into my vector. I can break up as 1/2 times 1, 0 plus -1 times 0, 1. And using the fact that linear transformations are awesome and they preserve scalar multiplication and vector addition, this becomes 1/2 L of 1, 0 minus 1 L of 0, 1. And I can start cooking up what this vector is going to look like by adding scaled versions of my long green and long orange vectors here. So this is going to end up being 1/2 of that thing, 2, 4. So we get half of that guy. Let's say that's about there. So half of that minus 1 times my long orange guy, which is -1, -3. So that becomes plus 1, 3. So going up 1 over 3. I was like, wait, that doesn't make any sense. We're going over 1 up 3. You can tell I'm an algebraist. I can't do space. All right, over 1 up 3. We get up somewhere like this. We add that on to here. And our new vector is vector addition. Okay, so that's one way to do this. We know we can break up linear transformations in terms of the basis, but I don't know, it's kind of annoying. So I want to calculate the eigenvalues and eigenvectors of this thing and draw a picture and hopefully convince you that in this case and in many cases, this is nice. When we have a diagonalizable matrix, this is really pretty cool. So, all right, here's my matrix A that represents my linear transformation with respect to the standard basis. And so let me calculate the eigenvalues of A by calculating the characteristic polynomial. All right, so we're going to take our characteristic polynomial, PA of lambda. We know, of course, that that is the determinant of A minus lambda times the 2 by 2 identity matrix in this case. So we're calculating the determinant of 2 minus lambda, -1, 4, and -3 minus lambda. And I think this arithmetic is going to work out. I checked it once on paper, so cross your fingers, it worked out nicely once. And we get this determinant. I get 2 minus lambda times -3 minus lambda plus 4. And of course, we want this characteristic polynomial to be equal to 0 because we want to find non-zero or non-trivial solutions to the equation ax equals lambda x. And we know that this equation can be rewritten as ax. Let's get rid of the x. With a little bit of elbow grease, we can rewrite this as a minus lambda I2 times x, and we want that thing to be 0. Now we know that this is going to be 0, that this is going to have non-trivial solutions if and only if the determinant of the matrix that we're multiplying by is non-zero. So that's why we're calculating the determinant and setting it equal to 0. We're trying to find out like which values of lambda is going to guarantee that we've got non-zero solutions to this equation. So this is kind of floating in the background, or I guess in this case in the foreground, informing what we're doing and why we're calculating the determinant and finding these lambdas. And why are they called lambdas? I don't know. Somebody liked sheep, I guess. All right, so let's simplify this guy. We're going to get -6 plus lambda plus lambda squared, right? Because I have plus 3 lambda minus 2 lambda, so that is going to get me a plus. Okay, that's good. That's how it's supposed to work. Plus 4. This simplifies down to lambda squared plus lambda minus 2, which I designed to factor. I want to draw pictures, and I'm not really good at drawing square roots of stuff. So let's factor this sucker. This gives us lambda minus 1 and lambda plus 2. So what we found is that if we want this thing to equal 0, this happens when lambda equals 1. And when lambda equals -2. All right, so from here, we go on and we calculate some eigenvectors. And I promise we're going to get to the Whygenvectors, but let's get the eigenvectors first so I can draw some pictures. All right, so we take our delightful eigenvalues. Let's take lambda equals 1 first. We are looking at the solutions to ax equals x, in this case, 1 times x, which means that we're looking for the null space of a minus 1 I2 times x. So let's take a look at so this is sort of like what's going on here. This is what we're looking for. And we want the non-zero solutions. We rule out 0 as an eigenvector because otherwise every real number scalar would be an eigenvalue, and that's not really too useful. Okay, so we're looking for the non-zero vectors in the null space of this matrix. So let's write her down. We've got 2 minus, in this case, lambda is 1. So 2 minus 1, -1, 4, and -3 minus 1. And that matrix is equal to sorry, I'm stumbling over 2 minus 1. You can tell it's a Friday. All right, so I got 1, -1, 4, -4. I want to get this thing into reduced row echelon form. So this will be row equivalent to the matrix. Oh, this is lovely. Look at that. That second row is a scalar multiple of the first row, so we can just kill it off. Oh, someone in my Twitter comments said that we can call this like the Eigenvalue or something because we're killing it off. It's you guys are great. Anyway, 0, 0, 1, -1. And that's our matrix in reduced row echelon form from which we can calculate the null space pretty quickly. Because remember, the solutions to the original matrix for this thing equals 0, we're going to have the same solution as 1, -1, 0, 0 times xy equals 0 because they're equivalent linear systems. So we see that from that first column, we see x and y are going to be the same thing. So we'll let y be any real number in R. Let's actually name it. Let's call it y equals r in R. We're not gonna let it be 0 because then we'll get that x is 0 too, which we don't want because we don't want a 0 eigenvector. And once we have that, the first row of this matrix tells us that x minus y is 0, so x is equal to y, which tells us that x is also equal to r in R, which means that our eigenvectors associated with lambda equals 1 are non-zero scalar multiples of 1, 1, right? Because they look like r times 1, 1, where r is a real number. Okay, cool. So this vector is pretty nice because what we know about this vector is that if I look at anything that points in the direction, roughly speaking, of 1, 1, so if it lies along that same line, when I apply my linear transformation to it, it's going to look exactly the same because it's a solution to ax equals x. So if I plot this green vector, what's L of that green vector? It's the green vector. All right, so let's go on and get our eigenvector for, or eigenvectors for lambda equals -2. And then we'll piece it all together to answer the big Whygenvectors question. So lambda equals -2. We have our matrix A. Let me just remind myself what it was. It was 2, 1, 4, -3, and I had a -1, and a -3 in there. So A minus -2in I2 is going to be A plus 2I2, which gives me the matrix. All right, 2 plus 2 is 4, -1, 4, -3 plus 4 is, -3 plus 2 is -1. And from here, we can get this into reduced row echelon form, or even just echelon form. Maybe I'll leave the 4 alone here, but we've got 4, -1, 0, 0. And what this tells me is I can I'll do this one orange, I can let y be any real number that's non-zero. And this tells me that x is going to be, or 4x is going to be equal to y. So if y is, sorry, I don't know why I'm stumbling over this here. So if 4x, let's see, so I've got 4 and 1 in here. Is that right? Yes, I think that's right. Because let's see, this tells me that y would be 1/4 and then x would be -1/4 y. I think it's backwards. I'm totally editing this part out in the actual thing. Okay, so I've got 4x equals y, which tells me that if y is 4, x is 1. So I'm looking at scalar multiples of 1, 4 for the eigenvectors associated with lambda equals -2 here. So for non-zero R, these are our eigenvectors associated with -2. And what that means is that if I plot something in the direction 1, 4, which is vaguely like that, when I apply L to that thing, what I'm going to do is I'm going to change it to point in the opposite direction and scale it out by -2. So I get a really long orange vector that goes like that. So it's L of 1, 4. And this is 1, 4. Okay, so Eigenvectors, why do we care about all of this stuff? Well, let's take that vector that we had earlier. What vector would we pick earlier? We picked the vector 1/2 and -1. So back to L of 1/2, -1. I want to write this thing as a linear combination of the eigenvectors that I've got, or the sort of principal eigenvectors that I've got here. So if I could write 1/2, -1 as a combination of, what was my first eigenvector? It was 1, 1. Oh, of course it was. All right, so 1, 1. and 1, 4, if I apply L to this thing, apply L in pink for change of pace, this is going to be super rad because I know that I preserve my scalar multiplication and addition. So I've got A times L of 1, 1 and B times L of 1, 4. I'm going to plug those back in. 1, 1, B L of 1, 4. And oh gosh, I know exactly what L does. I don't have to go drawing pictures. I can just write down the eigen stuff, right? L of 1, 1 is super easy to calculate because 1, 1 doesn't move. So this becomes 1 times 1, 1. That's associated with the eigenvector, eigenvalue 1. And L of 1, 4 becomes -2 times 1, 4 because that's associated with the eigenvalue -2. So really, we've got whatever A and B were, we're just going to take that combination of 1, 1 and -2, -8. So what we get is this thing is equal to A times 1, 1 plus B times -2, -8. And that's really nice because all we had to do was sort of scale the component vectors and the basis together. And that's going to be a really nice way to figure out what this is. So this is pretty delightful because it changes our problem from one where we've got to I don't know, pick a basis to one where it's like this basis that we are picking makes a lot of sense because it's the direction in which the linear transformation is the easiest to calculate. And so I guess we should go through the annoying process of figuring out what this thing is going to look like. Let's see, I want 1, 1 times A plus 1, 4 times B to be equal to 1/2 -1. And so if I write that in terms of this basis, and let's row reduce it. Oh, dare I row reduce it? I guess I dare. I've got 1, 1. Oh, why did I pick a fraction? Subtract the first row from the second row, and that's not equals. Bad Gibbons. Let's put our little row reduction arrow here. So I'm going to get a 0 and a 3 and a -3/2 here. And I'll row reduce this one more time. Permit me to be lazy and not write my row operations under these arrows, even though it's sort of bad form. I've got 1, 1, 1/2, and then 0, 1, -1/2 when I divide that by 3. And then I'm going to subtract row 2 from row 1 to polish this off. And so now I've got 1, 0, 1/2 minus -1/2 becomes a 1. And this is still 0, 1, -1/2. So this tells me, and hopefully I did this correctly, that 1/2 -1 is going to be 1 copy of 1, 1 minus 1/2 copy of 1, 4. Let's see, do I believe that? I sort of believe that. I get a 1/2 up top, and then I get 1 minus 2. Yeah, so I believe that. And so that tells me then the L of this thing, 1/2 -1, is the delightfully easy to calculate 1, 1 minus 1/2 times 2 times 1, 4. And I picked that 1/2 randomly, but gosh, it worked out really nicely because now this just gives us 1, 1 minus 1, 4. And so this thing ends up going to 0, -3. So that was pretty easy to calculate. I didn't need to do any fancy matrix multiplication or anything. I just know that my linear transformation is good when I plug in the vector 1, 1 and the vector, scalar multiple of 1, 4. Oh, except that was a -2. Shoot. Darn it. Okay, so close. Let's make that a plus. And so we get 2 and 5. It's not a real Gibbons video if there's not arithmetic mistakes in it. So there we go. Okay, so we got 2, 5 as our output when we plug in 1/2 -1. So if you've got, the machinery set up to do this row reduction quickly, or like with a computer or something, when you get your vectors in terms of the bases that come from the basis that comes from these eigenvectors, life's pretty good to calculate this linear transformation. Now, the question is like, can we always do that? Well, unfortunately, sometimes our eigen spaces, like sort of their dimensions add up and it's too small. And so we don't actually get a full basis, but you still get some like subspace where there's some good stuff going on. Anyway, that's a super fast Whygenvector example. It's just that it makes calculating the linear transformation really nice on certain vectors. And if you can take all of your vectors and write them as linear combinations of those, gosh, doesn't that sound nice? What an easy thing to do. All right, I hope that was helpful. I hope that answers some of the questions that my linear algebra class had. And if you sat through this whole thing, I hope you enjoyed it. I guess I should end with my favorite linear algebra joke, which is, hey, what am I drawing? And then, of course, you, good audience members, say, a sheep? And I say, no, it's a lamb, duh, because we're talking about eigen stuff. All right, peace out, everybody.